So here's another example of a projectile motion question. A ball is thrown from a height of 3.2 meters off the ground at an angle of 51 degrees above the horizontal. Hits the ground after 1.9 seconds. Find initial speed and distance it travels in the air. So we want to know initial speed, we know time, we know distance, we know initial height, so we know the delta y, we know theta, the angle, we know the time. Of course, we also know the acceleration, which is 9.8 meters per second squared downward. So if we want to find the initial speed, the simplest way to do that is using the time-dependent equation in the y direction. And we can just plug in what we know. We're going from 3.2 meters off the ground to ground height, so our change in height, 3.2 meters downward, or negative 3.2. Initial velocity in the y direction, well, that's the initial speed, the magnitude of the initial velocity, times the sine of 51, times time, 1.9 seconds. And again, our acceleration is 9.8 meters per second squared downward, so that is a negative 9.8 if we're calling down negative. Time again, it's 1.9. Right. So we can punch this into the calculator. We'd add this term to the other side, so we have negative 3.2 plus 0.5 times 9.8 times 1.9 squared. And then we're left with this. We need to divide out the 1.9 and the sine 51, so we divide by 1.9 sine 51. We get that our initial speed then is 9.8 meters per second. That was not intentional. That we would get 9.8. Oh well. Okay. Now, for part B, the distance it travels in the air, we do need to use the initial velocity to calculate that. So I'm going to go ahead and store that as v in my calculator. To find the distance it travels in the air, that's a two-part question. To find the distance it travels, we need to use the time-dependent equation in the x direction, but we don't know the time. Oh, we do know the time, so we can just plug it straight into the time-dependent equation in the x direction. Hooray, this is why it's handy to write down excuse me, the things that you know already. So we have delta x equals v naught x. Well, this is the magnitude of our initial velocity. I stored that in my calculator as v, so I'm going to write v. And then the x component would be v cosine 51, and time, we already know, is 1.9 seconds. So we plug those in, times cosine 51 times 1.9, and we get 11.73. With sig figs, that rounds to 12 meters. Alright, here's another example. We got a gun that's fired from 4.5 meters off the ground. This gives a bullet an initial velocity of 150 meters per second at 3.8 degrees below the horizontal. Find the distance it travels in the air, velocity as it hits the ground. Now this is different from the other problems we've done because this angle is below the horizontal. So what that means is that we've got this 150 meters per second, and that is at 3.8 degrees below the horizontal, like so. The only difference this makes is that the y component of our velocity then is going to be downward, which we typically call negative. So we're going to have to plug in a negative value into our y equations. I'll put that in. Other than that, it's exactly like problems we've done before. Distance it travels in the air, we can use the time-dependent equation in the y direction. Plugging in the values we know, from 4.5 meters off the ground, that's negative 4.5 equals initial velocity in the y direction is going to be negative 150 sine of 3.8 times time minus 4.9 times squared. 4.9 is half of 9.8. And you can then stick that into our graph, move the 4.5 to the other side, and it becomes 4.5 minus 150 sine 3.8 x minus 4.9x squared. We graph that, and we see that our bullet hits the ground very quickly, which makes sense because there's a bullet being fired downward at an angle. So makes sense that the amount of time it would take to hit the ground would be pretty small. That comes out to 0.38 seconds, and then we take that, plug it in to our time-dependent equation in the x direction. V naught x is going to be 150 cosine 3.8, and time is that 0.38, using the stored value, of course. So we take that value times 150 cosine 3.8, and we get 57.037, so about 57 meters is the horizontal distance it travels. And then if we want to find the velocity as it hits the ground, one point I want to make before we do this calculation is that if we think about this, the bullet's already going at 150 meters per second. So relative to that, the acceleration due to gravity is smaller than it often is. If I throw something with a velocity of 8.1 meters per second, well, a rate of, in 1 second, that velocity will have changed by 9.8 meters per second by 9.8 meters per second in the y direction, which is a more substantial change when my initial velocity was relatively small. As the bigger your initial velocities are, the less the acceleration due to gravity will affect the magnitude of the velocity. So just be aware of that. We'll see how much it changes. To find the final velocity in the y direction, we can use the time independent equation. Acceleration is 9.8 meters per second squared downward. The distance the bullet is moving is 4.5 meters downward. The y component of the final velocity is what we're trying to find. The y component of the initial velocity is 150 sine 3.8. Technically it should be negative, but it's squared, so it doesn't. The negative is going to cancel out anyway. But this negative is still there, so don't lose track of that. Don't cancel out these negatives. You need to square the value and then make it negative. So we've got 2 times 9.8 times 4.5, and then we are adding 150, whoops, not 105, 150 sine 3.8 squared, square root, the y component of the final velocity is 13.67 something. I'll store that value as y. The x component of the final velocity is the same as the x component of the initial velocity because there is no acceleration in the x direction. 150 times cosine of 3.8, which is 149 point something. I'll store that as x. And then we take square root of x squared plus y squared to get the magnitude of the final velocity. Turns out it's 150 meters per second. So actually, it didn't actually change significantly. It's 150.29 instead of 150. So as I said, the magnitude didn't wind up changing that much because it hit the ground pretty darn fast, 0.38 seconds. And see if the angle changed at all. Inverse tangent of y over x. Turns out it's at 5.2 degrees below the horizontal now. So the angle changed more obviously than the speed did.